All right, we're back. We're on page 2 of Notes 23 of Calc AB. We're talking about slope fields. Slope fields are really interesting. They're basically pictures of the solutions of differential equations. Why would you ever need this? Sometimes differential equations are more complicated than you can imagine at this point in your life. And knowing what the picture looks like, if you have enough experience, will tell you an awful lot about the solutions. So we're trying to develop this sense. There's a lot going on with these, and let's see if we can do this. So first thing we have to do here is we have to decide if x is in rows or in columns, and then if y is in rows or in columns. I'm going to say that x goes in rows because I feel like x is horizontal. I don't know. I like that. I'm going to put x here and put y here. All right, now our differential equation in this case is this. So dy dx is 1 plus x. What do you notice about that? Hopefully you notice there are no y's anywhere in there. So since there are no y's anywhere in there, really the slope is just dependent upon x. So as you move up and down vertically, you should get the same slope because x isn't changing, just y is changing. So let's actually do that. So x is equal to -2. The slope is going to be -1 regardless of what y is. So we get -1s everywhere. And I'll fill in the slope field after I fill in the chart, I think. If x is equal to -1, then dy dx is 1 plus -1 is 0, so we get zeros everywhere. So it doesn't matter what y is, you're getting 0 because x is -1. When x is 0, the slope is always going to be 1, regardless of y, which means you move up and down as much as you want on the vertical line x equals 0, the slope is going to be 1. Doesn't change. When y is, got that wrong. When x is equal to 1, the slope is going to be 2, 2, 2, 2, 2, and 2. And when x is equal to 2, the slope is going to be 3, regardless of what y is. So 3's across the board. 3's are my worst. I am the worst at making them. Look at all those 3's. They all look entirely different. It's like I'm training an artificial, it's like I'm an artificial intelligence that I'm training on 3's. All right, so when x was equal to -2, the slope is always -1. So I'm just going to fill those in. So when x is -2, the slope is always, so notice on this horizontal, nope, on this vertical line, x equals -2, the slope is always -1. I personally confuse horizontal and vertical a lot when I talk about them. Not physically, like I know this is horizontal, I know this is vertical. In class, I usually tell students, watch my hand because my hand is always doing the right thing, regardless of what my mouth is saying. But in this case, what are we gonna do? All right, so when x is -1, the slope is always 0. So let's fill those in. So this is a much more reasonable slope field to make. Even this slope field, though, has tons more points than you will ever really be required to do, but it's still good practice. When x is 0, the slopes are 1. So we just go for it. Along the vertical line, the slope isn't changing. Why isn't the slope changing? There's no y in the differential equation. It doesn't matter what y does, all based on x. When x is 1, the slope is always 2. So this is starting to get pretty extreme. You never really realize how extreme things are until you start doing slope fields, and you're like, wow, a slope of 2 is really steep. A slope of 3 is incredibly steep. So when x is equal to 2, the slope is 3, which means, I don't even know, so steep. I mean, you try your best. Okay, this is our slope field. Does it look like anything? Not really. I mean, it kind of looks to me. So I know if dy dx is equal to 1 plus x, I know that y is equal to, just integrate, right? It's going to be x plus 1/2 x squared plus c. So we just get a lot of quadratics that are all vertical shifts of each other, which if you now look at your slope field, can you imagine them? Can you like think of a quadratic? I think I can use like this laser pointer thing. Let's see. So like, I could have a quadratic that maybe does something like this, like something like that, or, this. Something like that. So these are the quadratics that you can kind of see. The key takeaway here, though, is our differential equation does not have a y in it. If there is no y in the differential equation, then along vertical lines, the slope will always be the same. So I think that's actually something that we're going to want to look for when we see a slope field. we'll be able to figure out right away, is there an x and a y in the equation, just an x, just a y? So if dy dx, oh God, that's not y. If dy dx is, I'm gonna say is a function of x, so I'm gonna say f of x, then there's no y in the equation. So the slope is the same along vertical lines. And then in parentheses, I'm gonna say x equals k, because sometimes I'm a dummy about vertical and horizontal lines. So, and then when you look at your slope field, that's exactly what's happening. There's no y in the equation. We could tell that now without having the differential equation. There's no y in this equation. Also, because the slope is always equal to 0 when x is -1, we know that x plus 1 is a factor of the differential equation. We don't know the whole thing necessarily unless we're given it, which we are in this case. But we do know, because the slope is always 0 when x is -1, that x plus 1 should be a factor. Look at the differential equation. It basically is x plus 1. So that worked out really nicely for us. These are the sorts of patterns. And you develop the intuition. Like, you don't walk in knowing all these things. That's why we're doing this. All right, let's do this one. So x, y. All right, our differential equation is this. Now, there's no x in this differential equation. So regardless of what x is, the slope will always be the same. So along horizontal lines, you can move left and right. You're not going to change the slope. Along horizontal lines, slope is always the same. Let's fill in our table. When y is equal to -2, the slope is 1 minus -2 over 2. So 1 plus 1, so 2. So 2, 2, 2, 2, 2. When y is equal to -1, we get 1 plus 1/2, so 3 halves, or 1.5, it just depends on how you want to look at it. I think that when you're dealing with slopes, fractions are the way to go. You might not agree with me. When y is equal to 0, the slope is just 1, because you get 1 minus 0, so 1. When y is equal to 1, we get 1 minus 1/2, so just 1 halves, all the way through. So this one it's equally interesting. If there's no x in the equation, it doesn't matter if you move left and right, the slope's not going to change. It's only when you move up and down that the slope is going to change. So did I say that right? It's only when you move up and down that the slope will change. Yeah, I did say that right. Okay. When I told you I was going to mess that up. When y is equal to 2, we get 1 minus 1, so we get 0. And you can see the slope, I mean, it's decreasing by 1/2 each time y increases by one, not by 1/2. All right, let's fill these in. So when y is equal to 2, the slope is always 0. So we're going like this. When y is equal to 1, the slope is 1/2. So up 1 over 2. So you just kind of aim. I'm aiming for 0, 2 right now. And then I'm just going to try to stay parallel. Those are hard to do. And then they're just going to get steeper. I mean, a slope of 1 isn't that bad. I mean, a slope of 1 is pretty much your default go-to slope when someone says, draw me something. And then we're going to get 3 halves. So it's like, I need to go up 3 and over 2. So I'm aiming for 0, 2 again. And then once I have one of them, I'm just going to try to maintain parallelism. Those are when I took English classes in high school. I think my teacher sometimes would like circle something and be like, lack of parallelism. Like I guess I'd mess up tenses or something. I don't know, the things you forget, man. So when y is equal to -2, the slope is always 2. So I'm actually gonna aim for, so I need to go up 2 and over 1. So I'm gonna aim for -1, 0, and draw that. That's looking very, did I mess one of these up maybe? No, I think it's just like hard to do. I mean, I also may have messed one of them up. I don't know. I think that's pretty good. I think I also may be messed up when y is -1. When y is -1, it should be 3 halves. So I want it to go up 3 and over 2. Nah, I think it's just hard to do. I think I like tried my best, and it's not enough. But I did my best. So along horizontal lines, slope is always the same. Why is that? There is no x anywhere in the differential equation. So we can say if dy dx is equal to a function of y. So I'm just going to say f of y, right? So you might say g of y. Some people do that, but like there's nothing sacred about f and x. Like they don't have to go together. It could be f of y, not a problem. There's no x in the diff EQ. So the slopes are the same along horizontal lines. So one of the things we want to do is we want to be able to match a differential equation to a slope field rather to its differential equation. So we're going to have to be able to say like, is this differential equation only a function of x? Is it only a function of y? Are both of them involved? You know, like things of that nature. One of the things that I do want to highlight though is you can tell that because the slopes are always 0 when y is equal to 2, seems like the differential equation should be something like a constant maybe times y minus 2, or so like that would have been my guess, right? So doing this problem, I would have guessed that dy dx is some constant that I don't know times y minus 2. If you look at the differential equation, it would appear that the constant is negative 1/2. Because if the constant is negative 1/2, I actually get what I was expecting. So you can guess, you can try to guess the differential equation. Sometimes you're going to be wrong. Sometimes you need to modify it a little bit. But looking for 0 slopes is seeming like a really good way to come up with these equations. And so we're actually going to be doing that a lot. We look for where the slope is 0. We look along horizontal lines. Are the slopes always the same? That means there's no x. We look along vertical lines. Is the slope always the same? If so, that means there's no x in the differential equation. 0 slopes, horizontal lines, vertical lines. We're building like a kind of a toolbox of how we're going to match our differential equations and our slope fields. So I'm done with this page. So I'm going to come back in the next video and work on the next page. So I will see you there.